Today's lesson is section 9.3, and you can tell by the title we're dealing with rational functions and their graphs. Well, what I've decided to do is there's quite a bit of information in this section, so we're really going to take 2 days. Today we're going to talk about analyzing functions, these rational functions, to determine certain properties. In particular, we're going to learn how to understand where the graph doesn't exist. In other words, we're going to lay out, before we start actually doing the graph, we're going to lay out any potential areas where we cannot graph. And that's, as you will be able to tell in just a moment, that's going to be the focus of today's lesson. And then tomorrow we'll go the next step and we'll put it all together and we'll actually start doing some graphs. So today no graphs, but we're going to look at some properties of these rational functions that will help us be able to do the graphs tomorrow. I showed the classes today an example just to give them a glimpse of what a typical rational function looks like when it's graphed. Not all of them look like this, but here's the rational function that you can see in blue. And what we're going to be doing today is looking at how we find these vertical asymptotes. There are 2 of them on this graph, x equals positive 2 and x equals negative 2. And maybe you can see that those 2 lines came from the fact that 2 and negative 2, when plugged in for x, make 0 in the denominator. And so what we're saying here is that these 2 lines represent ordered pairs where x is either 2 or negative 2. And since we cannot use 2 or negative 2 as inputs, then these 2 lines are basically off limits as far as our graph is concerned. We cannot graph on these 2 lines, and so they represent vertical asymptotes. And you'll notice we also have a horizontal asymptote. So part of the lesson today will be, how do we know if we have a horizontal asymptote, and if we do, where is it? And then you'll notice this other circle here that serves as a break in this parabola that's upside down in this other section. This is called a hole. And I'm going to show you today how you can know if you have a hole in a graph section, and if you do, where would it be? So all of these put together, vertical asymptotes, horizontal asymptotes, and holes, will be the focus of today's lesson, and all together they represent what your book calls points of discontinuity. In other words, if these lines, vertical and horizontal, and then this little circle here we call the hole, if they weren't here, then we would just have a graph that could just flow unimpeded forever and ever as you move from left to right. But since we have areas that we are not allowed to graph on because numbers that make 0 in the denominator, and then for other reasons we have a horizontal asymptote, these they cause our graph to have to be done in sections. And so today let's just look at how we find out how to find these points of discontinuity. So your first 4 problems on the assignment will involve pretty much doing this. When you're looking for points of discontinuity, you're trying to identify numbers that would plug in for x that would cause the denominator to become 0. So my first key point, as you can see there, is always factor if you can. That makes finding the points of discontinuity very easy. Alright, so the denominator does factor as x plus 1 times x plus 1. Now I can see in the denominator that when x is negative 1, it causes the denominator to become 0. And since we cannot divide by 0, then I know that I have a point of discontinuity when x equals negative 1. Okay, so if this were a problem in 2 through 8 even, you may have been given this function, then your answer would just simply be x equals -1, represents a point of discontinuity. That number plugged in for x in the denominator would create 0. Okay, here's some more, just practicing those types of problems, 2 through 8 even. Again, right off the bat, you need to think about factoring if it's possible. And we can factor here in letter A. That's the difference between two perfect squares. And then it's easy to just take a look at the denominator and identify numbers that would create 0. And there are 2 of them. When x is -4, I get 0 in the denominator, and when x is +4. So I have 2 points of discontinuity for letter A. Letter B, I'm going to go ahead and factor everything, but to be honest with you, in 2 through 8 even, the focus is really in the denominator. But it's a good idea for later on to just go ahead and get into the habit of factoring everything. So I'm going to look at the denominator, and I'm trying to find numbers that I could possibly plug in for x to cause the denominator to equal 0. Those represent points of discontinuity. Well, you can probably see that there aren't any numbers in this case. Any negative number that I put in and square it becomes positive, and a positive plus a positive is going to be greater than 0. And obviously that's going to happen when I choose a positive number. And here's another way of testing. If you look at a denominator and you're just not quite sure, you can always do this. Just set the denominator equal to 0, solve it, and you can probably see that we're going to get an imaginary number answer. And anytime this happens, you solve for x in the denominator, letting the denominator equal 0, and you get a result that involves the number I. That tells you that there is no possible way you could have an input that you could use for x and make the denominator 0. So therefore, on letter B, I'm going to say that there are no points of discontinuity. Remember, we're only worried about making the denominator 0. Some people have wondered, well, what about the numerator? Well, it's okay to have a number divided into 0. That's just 0. But it's not okay to divide by 0. So we're looking out for numbers that make the denominator 0. All right, and then this final example C, the numerator obviously doesn't factor, but the denominator does, as x plus 4 times x minus 2. Look at the denominator. There are 2 points of discontinuity. X is -4 and x is +2. So I've given you some samples of what you're going to do on problems 2 through 8 even. Okay, when you get to the next set of problems, 10 through 18, and then there's 4 more that I'm going to talk about at the end of this lesson. Here, we are going to start off in the same way as we did with the previous problems. I still want to identify points of discontinuity, so I'm going to go ahead and, for letter A, that's pretty nice. Everything's already factored out. So I'm just going to write down my points of discontinuity. But now, in these problems, we're going to go another step. We're actually going to give them a description. So these numbers that make the denominator 0 will either be vertical asymptotes or they will be holes. Now they can't be both. They have to be one or the other. And here's how you know. If the numbers, in this case 1 and -3, do not also make the numerator 0, and they don't. If I put 1 in the numerator, I don't get 0. And if I put -3 in the numerator, I do not get 0. Therefore, what I have here are 2 vertical asymptotes. So I'll just say that a different way. Vertical asymptotes are numbers that make the denominator 0 only. They do not also make the numerator 0. Well, a good contrast with letter A is letter B. Okay, here are my points of discontinuity. But if you notice, 2 not only makes the denominator 0, but it just so happens that 2 also makes the numerator 0. When this happens, that's when we have a hole in our graph. And I'll actually show you tomorrow how that fits in our graph, but for tonight I just want you to be able to find them. And then this other number, -3, it only makes the denominator 0, so we're going to label it as a vertical asymptote. Alright, so for letter C we've got a little factoring to do, so let's factor the numerator. And the denominator does not factor. Okay, identify numbers that make the denominator 0, and there's 1, x equals -1. And then just ask yourself the question, does -1 also make the numerator 0? And the answer to that question is yes. Therefore, x equals -1 represents a hole. Now I had some people today that said, well, is it also a vertical asymptote? Well, these numbers can never be both. They can only be one or the other. And since I've got one number that makes the denominator 0, and that number also happens to make the numerator 0, then our one point of discontinuity is labeled as a hole. Okay? So see if you can do that same thing on 10 through 18 even, and then the last 4 problems of the assignment. Alright, and then this is going to wrap it up. How do you know if we have a horizontal asymptote? And if we do have one, where is it? And so you might want to pause here, because this is something that needs to be in your notes. You're probably going to refer back to it. And if you need to pause the recording at this point just to give you a chance to write this down, this little table that I've created, that will be very helpful. Okay, so here's the deal about horizontal asymptotes, and I've given you a note here that I've said, I've phrased it, it's all about degrees. Well, here's what I mean by that. When you're looking for horizontal asymptotes, you're comparing the degree of the numerator with the degree of the denominator. The degree of the numerator in this case is 2. When you're trying to identify the degree, you're looking for the largest exponent for x. That is, if it's a polynomial. So the degree of the numerator is 2, and the degree of the denominator is 1. So I have presented here for you a situation where the numerator degree, that's what the n stands for, the numerator degree is bigger than the denominator degree. When this happens, you do not have a horizontal asymptote at all. So if this were a homework problem and I'm asked to find the horizontal asymptote, I'm going to say there is none. Okay, let's look at another case. In letter B, the degree of the numerator is 1. Remember, there's an invisible 1 exponent. And the degree of the denominator is also 1. Well, we have this situation where the degrees are the same. When this happens, you're going to make a fraction. And here's what I mean by y equals a over b. Think of a as the lead coefficient of the numerator, in this case -2. And think of b as the lead coefficient of the denominator, which is 1. Okay, so you can think of your horizontal asymptote being made by this fraction, y equals -2 over 1, which is another way of saying y is -2. Okay, so I did this in class today. Let me just go ahead and throw another example at you, because I don't want you to be tricked. Let's just say, for example, we had this rational function, and you probably already know this, but now you got to be careful here, because some people might just jump right in and say, let me make this a different number here. Okay, some people might just jump right in and say, oh, well, my horizontal asymptote is y equals 3/5. Well, hold on a minute, because if you notice, the numerator is in standard form, but the denominator is not. So when I say make a fraction out of the lead coefficients, I hope you understand that that means that both the numerator and the denominator should be in standard form. Okay, so you should be able to match up these lead coefficients. They should have the same degree, which they do. So actually, I'm going to have a horizontal asymptote, which will be the line y equals 3/4. 3/4. Okay, just want to make sure that you're clear on how to come up with that fraction when the degrees are the same. Well, the only other option, if the numerator's not bigger, if they're not the same, obviously the other case is, well, what if the denominator is greater? Or the way I have it here, the numerator is less. The numerator degree is 1, the denominator degree is 2. When this happens, then you always have the same horizontal asymptote every time. It will be the line y equals 0, which is another way of saying the x-axis. So just to refresh your memory on this graph that I showed you at the beginning of the lesson, do you see why we have a horizontal asymptote at the x-axis here? It's because the degree of the numerator of this function is 1 and the bottom degree was 3. Bottom is bigger. Therefore, we will when this happens, you will always have a horizontal asymptote, which will be the x-axis. Okay? So that is part 1 of section 9.3, and this is the assignment that you're going to do for the part 1 part. Now let me just make sure you understand, on these last 4 problems, the book is going to tell you to graph these. And we are going to graph them, we're just not going to graph them tonight. For tonight, I just want you to find all of the points of discontinuity. Do you have any vertical asymptotes, horizontal asymptotes, or holes? And just write them down. And tomorrow, then, when we get ready to graph, we'll already have this much of the work done, and we'll show you in class how to put it all together for constructing or sketching out the graph. Okay, so don't do the graphs of these, just come up with the points of discontinuity, just write them on your paper, and we'll talk about the graphs tomorrow. So I hope that helps you, and if you have any questions, just let me know, and we'll check them out tomorrow.